Hello, in this video, we will introduce Heap Sort. Heap Sort uses a binary heap. It first adds the elements to a heap and then removes the largest elements successfully to obtain a sorted array. The binary heap is a binary tree with the following properties. First, it's a shape property. It is a complete binary tree. Secondly, it's the heap property. Each node is greater than or equal to any of its children. So let's look at the complete binary tree. This is considered as complete binary tree is every level is filled except the last level. In the last level, all the nodes are filled leftward. So this is a binary tree, and this is also a binary tree, but this is not because this one, the last level, and this is not filled toward the left. So there's an opening here. This is not the complete binary tree because this level is not filled. So please note that this is it's a binary tree is complete, but it's not perfect. A binary tree is perfect. Every level is filled completely. So this one is a perfect binary tree. But this is, it's just this one here is V is a just complete binary tree. Now let's look at this animation here. We have this is a complete binary tree. It's also a heap. It satisfies the order property. This is the every node is greater than or equal to its children. So 80 is greater than 43 and 50. 43 is greater than 11 and 25. 50 is greater than 2. So this is yes. So let's add another one here. 45, 54 here. Let's add 54. So 54 is going to be here now. This is a heap. So this is what you see visually. A heap is look like it's a binary tree. So how do you store the heap when you write a program? It's very interesting. You can store all the elements level by level. So here's 62. 62 is right here. 42, 59, 31, 39, 44, 13, 22, 29, 14, 33, 30, 17, 9 in this order. So this is how you're going to store it. When you store it, you can just store it in a vector. So how do you know who is the parent, who is the left child or the right child? You know it from this property here is because it's a complete binary tree. So the parent is this, every node, for every node, the root is at position 0. So then the next one, the left child of the root is at index 1, and the right child is at index 2. So this is, look at this position here. So what is the parent for this 42? It is 1. So how do you get 1? It's this is the I minus 1 divided by 2. So I is this is the 1 minus 1 and divided by 2, that's 0. So what about this 22 at index 7? So look at this is I is 7, 7 minus 1, 6 divided 2 is 3. So that's how you get it. So this is the index of the parent for any element at index I whose parent is I minus 1 divided by 2. So what about the left child of 44? Left child of 44 is 30. So how do you know it's 30? It is this. It's this index 44 right here. The index is 5. 2 times 5 plus 1. So that is, this is 11. So 11 is right here. It's 30. So this is the left chart. What is the right chart for the element? This is the 44 is at index 5. So this is 2 times 5 plus 2. So that is 17. It's right here. It's 12. So this is really easy to determine who is the parent and who is the left child and who is the right child. This is very important in order to perform the algorithm for adding a new node and for removing the root. So when you remove the element from the heap, you always remove it from the top. So here is 80. So you can remove it. You always remove it from the top. That's 80. So when you insert it and you insert it, always insert it from here at this open position. So right here is 34. You're going to put 34 right here. And the next one, let's say you have 45. You put a 45 here. So insert 45. Now, this maintains the structure. It's still a binary, complete binary tree, but the order property may not be satisfied. So what you need to do is to compare 45 with its parent. So if not in order, swap it and all the way until it's ordered. So like here, now you insert a 45, 45 is going to be here. So 45 was here, then swap, and all the way you put 45 here. So that's how you do the insert. So let's look at this here. We're going to see how the insert here is. Let's insert something here is 88. So you're going to first put 88 right here. And then you compare 88 with 19. And then compare 88 with 22. So this is 20. This is the 88 is swapped with 22. So this is right here. So this is a complete diagram. You can see it. It's all this in one page. So how do you remove? When you remove, you always remove the root. So here we're going to remove this 62. So you remove 62, you need to maintain the property for the complete binary tree. So you're going to move 9 to the top and then compare 9 with the children. So this, whichever is the largest is swapped with 9. So this is 9 first, and then 59 swap with 9, and then 44 swap with 9, and then 30 swap with 9. So this is how you perform remove. Now we are going to have this design a class for heap. So we're going to use vector to store heap internally, and these are the two constructors. And this is remove, this is the add, and this is the get size. So here is the program. So here we have this is the type name T. So this is generic. Here is this the heap, And this is the another constructor. Constructor first is to construct empty heap. So this is the constructor heap with these elements from the array. So this is to remove, this is to add, and this is to get size is a const member. So internally, we're going to use vector of this type T for this V. So now this is the implementation for the Noaa constructor, and for this constructor we specify the array of elements. This is you perform remove. So you're going to remove it. This is if it's empty. So here, if this get size is equal to 0, so there's nothing to remove. So heap is empty. You're going to throw this exception. And now this is the remove it. So this is the element to be removed. It's the vector at the index 0. So now you need to copy the last one here. The last one is V. So the last, you're going to put the last one to this position. So what you can do is you can write this one here. So the last one here is this into right here, V0. And after that, you can remove the last one, pop the last one out. So this is, and then you're gonna just compare the root with the children, and so whichever is smaller, and you need to swap it with the root, and then continue this loop. So this is continue to go down and to compare the current element with the two children to find the smallest if needed to swap it. So that is here. So if there's nothing to swap, and then you're gonna break. So this is the code. So here's the add. When you add it, and you add it to the end. So starting from the last one, so you get the parent index. So here's a parent, and compare with parent to see if there's needed to swap. There's no need to swap, then you can break this loop. So that is for this implementation for the heap. So now we're going to use the heap to write the heap sort. So for this heap sort, first you're going to add all the elements from this list to the heap. So here's the heap, and this is the heap dot add it, add list brackets I. And now you're going to remove from the heap. So heap dot remove it from heap, and put it at the end of the list. So this is the array size minus I minus 1. So this is heap sort. Let's now analyze the time complexity for heap sort. So the time you're going to add this. So what is the time to add one element? It's dependent on the height of the heap. So let's look at the height. Let H denote the height of a heap. The height of a non-empty tree is the length of the path from the root to its furthest leaf. The height of a tree that contains a single node is 0. Conventionally, the height of an empty tree is -1. So this is the way, and we mathematically compute this height. We determine that the height is log n, order of log n. So this is the order of log n for the height. So the time complexity for adding one element is order of n. For add n elements is n log n. And for the remove, the same thing. it is remove one element from the heap, the time complexity is the height of the binary tree, so that is order of log n. And you remove n elements, so this time complexity is order of n log n. So the overall, the heap sort takes order of n log n time. That is all for this video on heap sort. See you on the next video.